Hi class, this is Sir Alex Basco and welcome to our lesson in General Physics 2. Today we are discussing a new lesson called Electric Fields. It's still a little bit related with our previous discussions, especially at lesson 3 and 4, where we measure and learn how to calculate and measure electric force. This time, instead of measuring electric force, we are going to measure electric field. So at the end of today's lesson, you will learn what electric field is and how to measure electric field. And Hi class, this is Sir Alex Pasco and welcome to our lesson in General Physics 2. We are opening a new discussion today, lesson 5, all about electric field. Previously, we've learned how to measure the electric force in, I believe, lesson 3. And we also learned how to use the superposition principle if we have multiple charges in lesson 4. Today, we are opening a new topic that is still a little bit related to electric force, but instead of measuring electric force, what we are going to measure is electric field. So at the end of today's lesson, what I want everyone be able to do is first to be able to calculate the electric field due to a system of point charges, and we are actually going to use the same law, Coulomb's law, as well as the superposition principle in order to solve for this field. But make sure I want to emphasize that this is electric field, not electric force. These are two different things, and I hope I will make that clear right now so you don't get confused on what we are measuring. So let's begin our discussion by thinking about these types of situation. So let's say if we got two positive charges. So if I'm going to draw, let's say let's have a green one. So if I'm going to draw a positive charge, green, and then let's draw another blue positive charge. There you go. What we know, and I hope everyone knows this, is that if we have two positive charges, like these two charges right here, the green positive charge and the blue positive charge, we know that these two charges will have to repel each other. This is something that we know. And we know that because they are two same sides. So there would be a force directed towards this way, which is a force that the blue, let's try blue, exerts on green. And then green will also exert a type of force directed to our blue charge. It's kind of different color. There you go. So green will also exert a force towards a blue. This is the force that green exerts on blue, and it's also directed on the opposite direction. We know that. We've discussed that. But the question that I want everyone to think now is, how does the blue charge seems to exert a force to the green charge and vice versa? How does this work exactly? Because the thing is that they are not touching without contact. We know in real life, if you want to push away someone, you have to use a physical contact. No? So kapag tinulak mo yung isang bagay, it will move. It will move away from you. Kapag hinila mo yung isang bagay, it will move closer to you. But how do these charges, these blue and these green positive charges, seem to exert the same type of force that we can do, but without physical or without having to contact with each other? How can we do that? So that's the thing that I want to emphasize now. They can do this via what we call electric field. Okay, so electric field is a physical field that surrounds an electrically charged object. Every charge has an accompanying electric field. So in order for me to kind of like draw what electric field is, we have to understand Michael Faraday's electric line force. So let's go back to our example right here. Let's say I have a charge right here. If I am going to draw a charge, let's say a positive charge, I know that this charge will actually have some type of electric field. going in all direction. It's surrounding this charge. And I'm going to draw this field that is surrounding my charge into lines to kind of like visualize my electric field. So you can think of these lines right here as the field itself. It's a physical field that surrounds a charge. And what does this field do is actually the one that is exerting the force onto the object. As long as you place, for example, let's say a charge within the field. So if I'm going to draw, it will keep having this type of force. Or again, this is a field, not a force, in all directions. And if I introduced, let's say, another charge, let's say there's a charge here, and let's also make it a positive charge. What will happen is this field that is surrounding this charge right here, let's call it our point charge. This is our point, or we can also call it as our source charge. So every time I say point charge or source charge, this is where the field, the electric field, is originating. And if I have this charge right here, what I'm going to do is I'm going to call it as my test charge. Test charge is the charge that is experiencing this field that is originating from my point or source charge. And then I get confused because this also has a type of field around it. It also has another electric field around it. But I'm not going to draw that, so the drawing wouldn't be messy. But also imagine there is also a field surrounding our test charge. But I'm more focused on this charge right here as my source of the electric field. So what is the relationship of the electric field and the electric force? Well, the reason that this test charge right here will experience, maybe let's use a different color, will experience a type force, will experience a type of force. I'm going to write it as FA. This test charge will experience this force, this repelling force, because of the surrounding field, the surrounding electric field of our source charge. So even if they don't have physical contact, the reason that this charge right here, our source charge, can push away our test charge and exerts a force, a repelling force, this Fe right here, is because of its surrounding electric field. And we visualize the surrounding electric field via electric line of force. This is the reason why even without contact, two charges can repel each other. Or even without contact, a negative and a positive charge would actually attract each other. And we can actually measure this electric field. Again, we're not measuring the electric force because we've done that. If I want to know how to measure this, I'm just going to use Coulomb's law. But this time, what I want to identify and what I want to measure is the electric field. How can I do that? Well, mathematically, we can measure the electric field, and we're going to use the letter E to denote electric field. Again, not F. F is usually the electric force. This time, I'm measuring electric field. If I want to measure the electric field at this point right here, one way that I can do that is basically get the magnitude of the electric force and divide it by to the charge that, or this charge right here, divide it, so take the force that this charge experienced and divide it to the magnitude of your test charge. So it's basically electric field is a measure of newtons per coulomb. It's the amount of electric force per charge. It's the amount of electric force exerted on this charge right here per its magnitude charge. So we know that the charge or the value of the charge of any point charge is coulombs, and we know that electric force is measured in newtons. In order for me to measure the electric field at this place right here, what I want to do is basically take the value or basically how much force does this test charge experience, divided it by the magnitude or the value of the charge of this test charge. So that's how we can measure electric field. Again, it's basically the amount of electric force per charge. Okay, so before we continue on and give examples on how we can measure this, let's try to understand more about electric line of forces. What are they and how we can use them properly? So there are different types of properties of electric line of force. 1. Electric field lines will always originate from a positive charge or somewhere in infinity. That's the, you could imagine that infinity as starting to have a positive charge, and will always terminate on the negative charge. What that means is the direction of my force will always start from a positive and will always end towards a negative charge. That will always be the direction of my electric field or my electric line of force. So if this is negative right here and I have a positive here, the direction would always be towards the negative. Another property of electric line of force is that there is a positive charge, or if there is a positive charge in its surrounding, electric field lines will be radially outward in direction and radially inward for negative charge. So let's say I have a positive charge right here. What that simply means, let's write it this way. There's no space. Okay. So radially outward. What this means is basically something like this. This would be the direction of my electric field. But if I have a negative charge, it will be radially inward. So this is how you would do it. Everything will be directed to the negative charge. This is the direction of your electric field. Okay? So again, it starts from positive and will end with negative. But if I have just, single one, I'm going to draw the electric field line or the electric line of force from a positive radially outward. They're all pointing outward. But if I have negative, they're going to be pointing inward. Next, electric field lines have a tendency of termination towards a negative. So that's kind of still like the first one. Charge. These lines will bend and terminate towards a negative charge. So if I have a positive charge right here and a negative charge right here, and we know that the positive will usually have a charge that is radially outward. They're all pointing towards outward. What will happen is these charges right here are not always straight. What they can do is they can actually bend. So I'm going to draw it something like this, and then can go something this way, and can go this way, and it can keep bending, something like that. So they have a tendency to always terminate on the negative charge. Hence, the line will always bend and terminates towards a negative charge. So they're not always going to be a straight line. They actually will bend. So that's another property of electric force. Another important property is that line of force can neither intersect or break. So what do we mean by that? So it's basically if I have a positive and if I have a negative here. Oh my god, let's... How can we do? Okay, so we know that positive charge will always have a direction that is radially outward, right? So the same thing here, they're radially outward. But what they're not going to do is going to intersect. This will never happen. What will happen here is they would actually bend in a way so that they wouldn't intersect. So they will never intersect, or I mean they will never cross. This will never happen. Or they will never break, meaning they will be continuous. So let me draw proper drawing. They will just keep. So they would be continuous. They would never break and then gonna continue, something like that. They would always so they will never intersect and they will never break. And another thing is that the greater number of line of forces, the stronger the electric field is. So if you want to denote a very strong electric field, just draw many line of force. And lastly, the neutral point is the point where no lines of force pass. Thus, the electric field in the area is zero. Neutral point is closer to the smaller charge. So let's go back to this picture right here. This point right here is called the neutral point. What this means is that there would be no electric field or electric line of force passing in this area. Again, we know this because electric lines of force cannot intersect or break. So this, if I have something like this, it will curve in a way so that these lines won't connect, because they will never connect because they're two positive charge. So if you have two positive charge or two negative charge, what would happen is it will result in a point where there's no electric line of force that can be here. And depending on which one is a smaller charge, so for example, this is a smaller one and this is a big one, this point of charge right here, this neutral point, will be closer to the smaller charge. So those are some of the properties of electric line of force. Now let's continue our discussion with electric field. Let's understand more about the relationship of the electric force and the electric field. So if I have a situation going on right here, so I have some positive charges on top, and if I have negative charges on top, we know that the direction of the electric field would be going downwards because they always start at the positive and will always terminate at the negative. So the positive charge will experience an so if I have a positive charge, it's right here. And let's draw a negative charge here. Maybe let's change the color so we don't get confused. There we go, I have a negative charge there. The positive charge will experience an electric force that will be directed in the same direction as the electric field. So again, this will always gonna be true. The direction of the electric field will always be positive to negative. But if I introduce a positive charge within this field, so this area right here is the field of electric field. It's an area with an area with electric field. If I introduce a test charge, a positive test charge, what will happen is that this positive charge will experience a force that would be on the same direction of the electric field. But if I introduce a negative charge within this electric field, what would happen is this negative charge will experience a direction of force that is opposite to the direction of the electric field. So just remember that if you have an electric field and you introduce a negative charge, the direction of the electric field and the direction of the electric force should always be on the opposite direction. And if I have a positive charge, the direction that the positive charge will experience will always be in the same direction of the electric field. And we can measure the magnitude of this electric field by taking the magnitude of the forces for each of this test charge. So take that and then identify, you just need to identify the magnitude of the charges of these test charges, and then you just have to divide the test charge to the magnitude of the electric field, or to the magnitude of the electric force, to find the magnitude of your electric field. So now that we understand the direction and we understand more about what electric fields are, let's discuss how we can measure more about the electric field due to the point of charge. Okay, so review, we know that electric charge creates an electric charge, or any charge creates an electric field. And we know that electric field, we can measure it this way. E is equals to the force divided by the value of the charge. To solve for the electric field, at any given point of the distance r in space from a point charge, again, point charge is a source charge. Imagine placing a test charge Q0 or Q0 at that point in distance. Using Coulomb's law, we know that the magnitude of electric force would be going to be this way. Okay, so if I draw the situation right here, let's draw it first. Okay, so to solve for the electric field at any given point at the distance r in a space from a point charge Q, so let's use our black. There we go. So if this is my Q, this is my point charge or my source charge. This is where the field is originating. So, and then if I want to measure the electric field at any given point at the distance r, what we can do is imagine placing. So what that means is, for example, at this point right here, what is the electric field at this point? Okay, so let's imagine this as positive. So it would have some amount of electric field that is directed radially outward. So it's kind of like going everywhere. Okay, so what I want to do is, what if I want to measure the electric field at this point? So there is such a distance between this point, and we're going to call that distance r. So there's a distance from my point charge to this point right here, and I want to measure the electric field at this point. Okay, what I'm going to do is I'm going to change this point and I'm going to add a test charge. Usually test charge could be positive, and what I can do now is using the Coulomb's law, we can measure the electric field. Because we know that the electric field is equals to the force experienced by the test charge divided by the magnitude of the charge of the test charge. And if we separate these two, Fe multiplied by 1 over Q0, this is basically the same, I just removed Fe. And we know Fe is basically the electric force, and we can measure electric force using Coulomb's law. This is our Coulomb's law, where we have a constant, Coulomb's constant divided by Q1 or Q0, which is our test charge or our source charge, and our second point is our Q0. Okay, and what we can do is divide it by the distance between the two, which will give us r squared all over 1 over Q0. And then we can remove those, so that cancels. What we are left with is this equation right here. So what we can do to measure electric field is we can use the columns law, but so we just edited it a little bit. So instead of using the value of Q0 now, we have to know the value of the Q here divided by the distance between the two charges is squared, and we just have to multiply it with columns constant, and we can find E. So there's two ways to find E. One is to identify the force experienced by the test charge, this Q naught right here, divided by the magnitude of the charge of Q0. Or we can also measure the electric field by taking the columns constant, multiplying it by the charge of the source charge divided by the distance between the two. So this is the whole equation that we have. Now let's try some of our sample problems. Let's move on to here. There we go. So sample problem 5.1. Calculate the magnitude and direction of the electric force field 0.45 meters from A 7.85 times 10 raised to negative 9 coulombs point charge. Okay, so how are we going to do this? Let's first write our given. Okay, so what we want to do is they give us, so direction of the electric field 0.5 meters. So they gave us the distance. So we have a distance of 0.45 meters. And there you go. Let me rewrite this to smaller. Okay. So our first given is they gave us the distance between our source charge and our test charge, point or source charge. So that would be R is equals to 0.45 meters, and they gave us our Q, which is equals to 7 or positive 7.85 times 10 raised to negative 9 coulombs. And what is being asked is calculate the magnitude and direction. So what we want to do is find the magnitude as well as the direction of our electric field. So the equation that we have to use, or the formula, is basically E is equals to coulombs constant multiplied by, just you have to remember this, the absolute value of your magnitude of your point charge divided by R squared. So very similar to Coulomb's law. Instead, in Coulomb's law we have two of this, but this time for electric field we only have one. So let's solve for this. So we have E is basically equal, the Coulomb's law is equals to 9 times 10 raised to 9 Newton meter squared per coulomb squared. All of this multiplied by the absolute value of our point charge, which is 7.8 times 10 raised to negative 9 coulombs, divided by R, which is 0.45 meters squared. And if you plug in that on your calculator, you would see here that our M is cancelled and one of our C is cancelled, and that would give us newtons per coulomb, which we know should be the unit for our electric field. So just plug that up on your computer, you would get 348.89 newtons per coulomb, or that is actually equivalent of about 350 newtons per coulomb. Okay, so this could be your answers right here. So it's still quite easy. So let's try our next sample problem. But I hope it's clear. If you guys have any questions about this, do not hesitate to message me. Now let's move to our next sample problem. Okay, so this time what we have is an electric dipole. An electric dipole consists of two equal but unlike charges separated by a distance. 2 point charges Q1 is equals to positive 4.5 times 10 raised to negative 6 coulombs, and we have Q2 which is equals to negative 4.5 times 10 raised to negative 6 coulombs, are separated by 6.4 times 10 raised to negative 6 meters, forming an electric dipole as shown in the figure below. Figure the electric field halfway between the dipole. So what we have is a dipole right here. We know, according to the problem, that a dipole, an electric dipole, consists when you have two electric charges that are equal in magnitude but just unlike signs. So what we are looking for is at this distance right here, what would be the electric force at the distance right here. So how are we going to solve this? What we're going to do first is we're going to write our given. So for our first given, they gave us the charge of our Q1, which is a positive charge of 4.5 times 10 raised to negative 6 coulombs. And they gave us our second charge, which should be equal in magnitude but only opposite in sign, which is negative 4.5 times 10 raised to negative 6 coulombs. And they gave us the distance between the two. The distance between the two is 6.4 times 10 raised to negative 2. Let me confirm that. Yeah, this should not be negative 6. This is just negative 2. Okay, so negative 2 meters. So how am I going to solve for what is being asked, which is figure the electric field. So what is the electric field halfway? So what would be the electric field in the middle of these two charges? So we discussed earlier that in order for us to figure out any electric field at any point that is within the vicinity of any charge, we can use the equation E is equals to K plus or K multiplied by the charge of your point charge or your source charge divided by R squared. Okay, so let's stick to this formula first, and later we have to use another formula, this formula right here. I'm gonna explain why later, but we're going to use this formula later for finding the direction. Okay, so what we're going to do is we're going to use these equations right here to solve for the electric field at this point. Okay, so since the question is asking us for the electric field halfway between the 2 point charges, we begin by, what we're going to do is imagine that at this point right here, we have a test charge. So this would be our test charge. So let's put a test charge right here. And usually, so that we wouldn't get confused, just use a positive test charge. So we're going to put a test charge in the area where we want to find the electric field. And then what we're going to do is we will have to compute the electric field due to Q1 and due to Q2 that is being experienced by our test charge. So let's begin our solution. So let's find the electric field that is originating from our Q1. So in order for us to solve that, that would be equals to K multiplied by Q divided by R squared. So the value of K is 9 times 10 raised to 9 Newton meter squared per coulomb squared, multiplied by the absolute value of our Q1, which is positive 4.5 times 10 raised to negative 6 coulombs, divided by our distance, R squared. but our distance is halfway. This distance right here is the distance between Q1 and Q2. But we're looking for the electric field at this distance. So what we're going to do is get the value halfway. Sorry about the rain sound. So we're just going to divide this by 2. And this is actually equals to 3.2 times 10 raised to negative 2 meters. So this would be 3.2 here times 10 raised to negative 2 meters squared. Okay, and just plug that up on your calculator and you would get that the electric field exerted by Q1 or originating from Q1 at this point right here is actually equal to 3.96 times 10 raised to 7 newtons per coulomb. So the meters get cancelled. One of the columns gets cancelled, so you're left with newtons per coulomb. So that is the electric field exerted by Q1, originating from Q1 at this point right here. That is the magnitude of the electric field. Next, we're going to find the electric field by Q2, which again is also equal to this equation. And if you actually notice, they are basically the same equation because we're using the absolute value for Q. So even if this is negative, we still have to use 4.5 because we need to use again the absolute value. And it's the same distance anyway because we're looking halfway between the dipoles. So the distance between Q1 would be equal to the distance for R2. Okay, so that will give us 3.2 times 10 raised to negative 2 meter squared. So our meters get cancelled. One of our columns here gets cancelled. We're left with newtons per coulomb. And this is still equals to 3.6 times 9 raised to negative 7 newtons per coulomb. But we're not done yet because we're looking for the electric field here, but there are 2 point charges. If we only have 1 point charge, then this is enough. But since we have 2 point charges, we have to identify the force or the electric field here as because of 2 charges. So we know from the line of force that Q1 will repel. So we know from the line of forces that Q1 will repel Q0 or Q0. We know that because our test charge is positive. So when you add a test charge on anything, it's always going to be positive. So what will happen is Q1 will repel Q0. And we know the charge Q2 will attract Q0. Hence, we know that E2 is directed to the right. We know that E2 is directed towards the right, because it will attract Q0. And we know that Q1 is let me check. Yeah, Q1 is also directed to the right because Q1 will repel Q0. So Q1 will repel Q0 going this way, and Q1 will attract Q0. So they're both going this way. So they're both going in the right direction. So according to superposition principle, in order for us to find the magnitude of the electric field at this point, all we have to do is add all the individual electric fields. So this still follows the superposition principle. So the total net force is equal to E1 plus Q. So this is where this equation comes from, because we're looking for the total E here. If you only have one charge, this is the answer. But since we have two charges, we have to we have to consider the two charges. So the total electric field, the total magnitude of the electric field would be equal to 3.96 times 10 raised to 7 newtons per coulomb plus 3.96 times 10 raised to 7 newtons per coulomb. And we're adding them because they're both directed to the right. So the direction of E is positive and the direction of E is also positive. But this direction, this sign right here is totally up to you. If you decide that direction to the right is negative, you can use a negative. But I decided, since they're going right and right is the positive x, I'm going to use positive sign. So the total E net is actually equal to 7.92 times 10 raised to 7 newtons per coulomb directed to the right. There you go. So that is the answer for our question. So what is the magnitude of the electric field halfway between our two charges? Is 7.92 times 10 raised to 7 newtons per coulomb directed to the right. So I hope that is clear. Let's get on to okay, what we are going to do is, so that our time won't be too long, I'm gonna cut the lesson and there will be second part for this video. So we're gonna end our video now and just go hop onto the next video after. Okay, see you guys in the next video.